Welcome to the Chapter 7 review questions. As normal, I'm not going to be doing the question 1 because it's just vocab terms, but for this chapter, there's actually only 2 that you have to learn. So we're going to start with question number 2. Question number 2 asks, how many molecules are in a mole? We'll actually have that up here. And it is a number that you should be learning called Avogadro's number. And there are 6.02 times 10 to the 23rd molecules in a mole, atoms in a mole. So for question number 3, it says how many atoms are in 58.93 grams of cobalt. Cobalt on your periodic table is a transition metal, and it's up here on this top row, and it is atomic number 27. And you'll actually notice on your text that below it in the periodic table is this exact same number. That's that number we were using in atomic mass units, and it's also that number that we use for molar mass. And that tells me that this is the mass of 1 mole of cobalt. So if 1 mole of cobalt weighs 58.93 grams, I know in 1 mole I have 6.02 times 10 to the 23rd atoms. So if you were to mass out 6.02 times 10 to the 23rd atoms of cobalt, you would have 58.93 grams. For question number 4, you're going to have 3 parts, and in each of those parts, you're converting from a sample into moles. And so you're going to get a lot of practice converting into moles in this chapter. And so for part A, it says I'm starting with a 100-gram sample of iron. And so for these questions, they're going to get longer, but I always say and tell my students to write down what you know or what you're starting with. And I'm wanting to cancel out grams of iron, so I'm going to put grams of iron on the bottom, and I'm going to moles, so I'm going to put moles on the top. Now the number that I use to convert between moles and grams is that molar mass is going to come from your periodic table. For iron, it is 55.85 grams. So when you put this in your calculator, you're going to say 100 divided by 55.85, and grams of iron will cancel out and you're left with your unit in moles. Since I have 4 significant figures here, and I also have 4 significant figures in that measurement, my answer, I'm going to report it with 4 significant figures. Question 4, part B, gives me 250 grams of methane, and I am trying to convert this to moles. So I'm going to start with what I know. And I'm going to want grams on the bottom to cancel out, and I'm going to moles, so I'm going to put mole on the top. Now, methane, or CH4, is not on the periodic table in the text, but a carbon is, and so are hydrogens. So to calculate the molar mass of methane, or CH4, you're going to add up the masses for a carbon and 4 hydrogens. For carbon, it's 12.01, and then we actually have 4 1, 2, 3. We have 4 hydrogens. And so when you add all of this up, you're going to get the molar mass of methane, which is 16.05. And so that is grams per mole of methane. So when you put this in your calculator, you're going to say 250 divided by 16.05. And grams is going to cancel out, and you're left with your answer in moles. And you end up with 15.58 moles of CH4. And I'm going to report my answer with 4 significant figures because I have 4 significant figures of each of the data that's going in. Question 4, part C, is the same thing. We're going from grams to moles. So go ahead and try this one by yourself. So for this one, you're going to have 500 grams of KiO3. And we're going to be putting grams on the bottom and moles on the top. But like in the past one, we don't know the molar mass of KiO3, so we have to add that up using the numbers from your periodic table. So you'll find on your periodic table that a potassium has a mass of 39.10, and you're going to be adding an iodine to it, 126.90, and then you're also going to be adding 3 oxygens. Each oxygen is 16, so 3 times 16. So when you calculate that, you're going to be getting the mass of this compound to be 214 grams per mole. So grams are going to cancel out, and we're going to be ending up with 2.336 moles of KiO3. Question number 5 has 3 parts also, and it is almost identical to question number 4. We're just working in the opposite direction. And so instead of going from grams to moles, this time we're going from moles to grams. So for part A, it tells me I'm starting with 14.5 moles of strontium. Since strontium is an element on the periodic table, I don't have to do the math to calculate the molar mass of the compound. I can just look it up on the periodic table. Except this time, since I'm going to grams, I'm going to be putting grams on the top, and I'm going to be putting moles on the bottom. From my periodic table, I get a molar mass of strontium of 87.62. And moles is going to be canceling out. And since 14.5 and 87.62 are both on the top of my problem, I'm just going to be multiplying those numbers across. And when I do that, I get 1,270 grams of strontium. So let's do that again for part B. 5B, I have 0.045 moles of calcium sulfide, and I'm going to grams. Now this is a compound, and so I'm going to have to calculate that molar mass of calcium sulfide. So I'm going to do that by taking the mass of 1 calcium and the mass of 1 sulfide and adding them together. From my periodic table, I know that calcium has an atomic mass of 40.08 and sulfur has an atomic mass units of 32.06. So when you add them together, you get a total mass for the compound of 72.14. Now, even though I just said atomic mass units, this is also molar mass, which is the same as grams per mole. Sometimes I'll leave that E off of the mole. So let's take 0.045 moles of calcium sulfide. I'm going to put moles on the bottom so it cancels out, and I'm going to put grams on the top. So I know that I have 72 goes next to the grams, and that is going to be your math that you're going to be doing. So you're going to take 0.045 and multiply it by 72.14. And you get 3.2 grams of calcium sulfide. I'm only going to be reporting my answer with 2 significant figures, because if you'll come up here, I only have 2 significant figures in this measurement. For 5C, we're doing the same thing. So test yourself. Stop and do it yourself and come back and check it to me. What we're doing for this is we're taking 0.876 moles of magnesium sulfate, and we're wanting to know how many grams that is. Now, magnesium sulfate, you may kind of be familiar with this. This is the compound that is in Epsom salts, if you've ever taken like an Epsom salt bath for sore muscles. So when we look at magnesium sulfate, you're not going to find it on the periodic table because it's a compound. So we need to find the molar mass of 1 molecule of magnesium sulfate by looking at your periodic table. The mass of magnesium is 24.31 atomic mass units. We're going to add it to a sulfur. The sulfur is 32.06. And then we're going to do 14 oxygens at 16 atomic mass units each. And so when you multiply and then you add those together, for the compound of magnesium sulfate, we get 120.37 atomic mass units or grams per mole. So we're going to start with what they gave us of 0.876 moles. And I'm going to put moles on the bottom so that moles cancels out, and grams on the top because that's what I'm looking for my answer for. So when you say 0.876, you're going to multiply it by 120.37. And when you do that multiplication, you get 105 grams of MgSO4. Since this measurement has 3 significant figures in it, I'm going to be reporting my answer to 3 significant figures. Question number 6 asks, how many atoms are in 100 grams of lithium? Now, this is a 2-part problem and it frequently stumps students. But if I only have 1 bit of information that they gave me, and that's 100 grams of lithium. I don't know how to go from grams of lithium to atoms, but I do have a conversion factor that will take me from grams of lithium to moles of lithium, and then from moles of lithium, I can use Avogadro's number to go to atoms. So this is a two-part problem. You can actually do this problem in two separate steps, or you can do it in one long step. I prefer to do it in one step, but if you want to split it up, that's perfectly fine. So to go from grams to moles, you're going to be using that molar mass from your periodic table. So you're going to be looking on the periodic table and finding lithium. And it is 6.94 grams of lithium is 1 mole. So grams is going to cancel out, and I'm left with moles. Now, if you were doing this in two separate steps, you could go ahead and solve this and then do the next step. But I'm just going to do it in one motion. So now I'm going from moles to atoms. So I'm in moles. So I'm going to want to put moles on the bottom, and I'm going to atoms. The reason I put moles on the bottom is so moles will be canceling out. And I know that there's 6.02 times 10 to the 23rd atoms in 1 mole. So moles is going to cancel out. And if my units work out right, or my units cancel out correctly, I can be confident that my answer is going to be correct. So grams is canceling out and moles is canceling out, and I'm left with an answer in atoms. Now, to put this into your calculator, you can do this, like I said, in two different steps, or you can do it in one motion. And so you would multiply everything on the top in parentheses, and then you would divide it by what is on the bottom. And you should get 8.67 times 10 to the 24th atoms of lithium. For question 7 is another two-part stoichiometry problem. One of the things I frequently tell my students is if they get through these and they don't even know where to start, the first thing is to take the number that they give you and to convert it to moles. So this question, though, is asking me how many molecules are in 50 grams of phosphorus trihydride. And I have grams, and I'm going to molecules. But if you'll remember, I can't go straight to molecules. I have to first convert from grams to moles, and then from moles to molecules. So this is another one of those two-step problems. So I'm going to start with grams, and I'm going to convert to moles. I'm going to put grams on the bottom and moles on the top. Now this is that molar mass problem where I'm going to get this number from my periodic table. So I need to look up what is the mass of 1 phosphorus and the mass of 3 hydrogens. So when you add up 1 phosphorus and 3 hydrogens, I'm not going to show you through every step of that way, but you get 34 grams. So grams cancels out, and I'm in moles, but I'm trying to get to molecules. So I'm going to put moles on the bottom, molecules on the top. Now I know how many molecules are in a mole. Oh, I didn't leave enough space, but it's okay. There's 6.02 times 10 to the 23 molecules in a mole. So my moles are going to cancel out, and I'm left with my answer in molecules, which is what I'm looking for. So you're going to say 50 times 6.02 times 10 to the 23rd, and you can divide it by 34. Or you could say 50 divided by 34 times 6.02 times 10 to the 23rd. Play around with how you like to put it in your calculator. Different people do it different ways. Just make sure that you're following the PIMBUS rules or the order of operations correctly. When you do this, you get 8.85 times 10 to the 23rd molecules of pH3. It is so important that you show your steps, that you cancel out, you show canceling out of your steps, and that you keep your units in your answers. Because this problem only has 2 steps, but we're going to get to some of these problems that have upwards of about 6 steps and possibly even more. And so if you're not somebody that shows your work or you don't keep your unit, your math is going to lend to lots of silly mistakes. And so to eliminate those mistakes, show your steps and show how you cancel out your units, and that will help make sure that you try to minimize those sources of error. Question number 8 says that a chemist has 1.0 times 10 to the 23rd or 22 molecules of water. It has two answers. It's asking, first one it's asking for how many moles, and then it's asking for how many grams. So I'm going to have to solve this one in 2 steps so that I get both answers. So the first one, you're going to start with just the only number they gave you, and it's molecules of water. And we've talked about how if you don't know what to do, you convert to moles as your first step. If I have moles and I'm wanting to cancel out molecules, I'm going to be using Avogadro's number. Molecules is going to be canceling out, and I'm going to get an answer that's going to tell me how many moles of water I have. Make sure that you're putting parentheses around both of these as you put them in your calculator. You get 0.017 moles of water. I have 2 significant figures here, so I'm only going to be using 2 significant figures in my answer. There's 2 sig figs here, and there's 3 here, so I'm going to use the one with the least amount in my answer. Now, from moles, I'm going to go ahead and I'm going to solve the second part where it asks for it in grams. For moles to grams, moles is going to go on the bottom and grams is going to go on the top. Grams is going to come from the periodic table. You're going to look and you're going to find 2 hydrogens and 1 oxygen. So oxygen is 16 atomic mass units and each hydrogen is 1.01. So you would have 1.01. So water, 1.01 plus 1.01 plus 16 equals 18.02. And that's something actually we'll probably use enough that you may learn the molar mass of water because you'll get tired of adding it up. But moles cancels out and you're going to be left with your answer in grams of water. Here we have 2 significant figures and 4 significant figures, so I'm going to report my answer to the least amount, which is 2. So you end up with 0.31 grams of water. So if you were to mass out 0.31 grams of water, you would have this many molecules of water molecules. Question number 9, you may actually do a similar lab to this, but it says the hydrate of magnesium sulfate. So we talked about magnesium sulfate being Epsom salts that sometimes you can put in your bath water. And a hydrate is a compound that has water molecules bound to it. Is it a liquid? Is it like a liquid water? No, this is actually a crystal that for every magnesium sulfate molecule has 7 water molecules in it, but it is a solid. It looks like that solid Epsom salts. And so it has 7 for every molecule. So I want you to write the formula for the hydrate version of magnesium sulfate and then write it again for the anhydrous. So for the hydrate, it's gonna look like magnesium sulfate, which is what it gives you in the problem. And then it tells me there's 7 water molecules for every one. And so you're just gonna write, it's like times 7 and then H2O. The other vocab word that you have is anhydrous, and that is when it doesn't have the water to it, and that's MgSO4. And hydrates will absorb this water on your own. If you just leave them out, it will actually absorb this water from the atmosphere. All right, so question number 10 refers back to question number 9. It says a student has 100 grams of this MgSO4 anhydrous, which means it doesn't have any water, and it wants to know how many grams of water can it absorb. Now, if you'll remember this formula I gave you of 7 waters, this is not for grams. This is telling me for every 1 mole or 1 molecule of magnesium sulfate, you're gonna have 7 water molecules. That's not converted in grams. So I need to know how many moles or molecules I have of this, how many molecules I have of MgSO4, so I can know how many molecules of water I need. Now I know that I have 100 grams. I want to know how many moles that is. So you're going to put grams on the bottom and moles on the top. This one's kind of a tricky problem, so if it's really confusing, it's okay. And you're gonna need to know the other thing you're gonna have to calculate is the molar mass for a magnesium sulfate. You're gonna get that by looking all of those up on the periodic table. On question 5C, we already calculated it to be 120.37 grams per mole. So grams will cancel out, and I'm left knowing how many moles I have of magnesium sulfate. I know that I have 0.8308 moles of magnesium sulfate, and I also know that there's 7 water molecules for every one of those. So if I take 0.8308 and I multiply it by 7, that's going to tell me how many moles of water I have. I'm going to show it to you just writing it out, like using the factor label method to stick with it here. So 1 mole of MgSO4 goes to 7 moles of water. Question doesn't ask me for moles of water, but I get 5.816 moles of water. The question's asking for grams, how many grams? So we can easily convert from moles to grams. So I'm going to put grams on top of water and moles on the bottom. That way they cancel out, running out of space. If you'll remember, we said there's 18.02 grams of water, so moles cancel out. Now if you say 5.816 times 18.02, you get 104.8 grams of water. I know it's really messy and I ran out of space. Y'all are used to that by now. If I was to have 100 grams of magnesium sulfate, remember we've said if you're lost, you don't know what to do, convert it to moles. So that's the first thing I did is I converted my magnesium sulfate to moles of magnesium sulfate. I also know that 1 mole of magnesium sulfate reacts with 7 of water. So for every one of these, I'm adding 7 moles of water. So I took how many moles of magnesium sulfate and I multiplied it by, because magnesium cancels out, 7 moles of water. And that tells me exactly how many moles of water I'm adding to this. But the question doesn't ask for moles, it asks for grams. And so this is this last step. We're using the molar mass of water and we're converting this from moles to grams of water. Question 11 kind of refers to an experiment I hope you get to do in lab. It says you have anhydrous version of cobalt chloride and you're gonna just like leave this out on the counter and it's absorbing water and it's becoming hydrated. And it's wanting to know if this is a physical change or a chemical change. Well, if you do this in lab where you actually have a sample, but you heat it up and you drive all the water out, it changes colors. And if you actually let it sit on the counter for a while, it will absorb the water back into it and become hydrated again. And so this is a reversible. So if you'll remember, a physical change is usually something that can be reversed and a chemical change cannot. So this is going to be an example of a physical change. In the end, I still have cobalt chloride. I have not chemically changed this compound. It has just gained some water. Question number 12 gives us a formation reaction. If you'll remember, a formation reaction is when you take parts of something and you add it together to form a new compound. And a few things about this is I have 2 homonuclear diatomics. Here I have hydrogen and oxygen, and so that's why you just have H2. And you have O2, and we don't have just, my students will freely want to just put O because there's 1 oxygen here. We have to remember oxygen is never found just by itself, and the same with hydrogen. So the question is asking us, it says we have this compound, and I am wanting to make 100 moles of this. If I want to make 100 moles, how many moles of hydrogen do I have to start with, and how many moles of oxygen do I have to start with? So it's taking a recipe. It's saying I need to make this much. So what do I have to start with so that I can make that much? I'm going to start with what I know, which is 100 moles of CH4O. And I'm wanting to go from moles of CH4O, we'll do the first one, to moles of hydrogen. And so since I'm gonna put moles of CH4O on the bottom so it cancels out, and I'm gonna put moles of hydrogen on the top because that's what I'm going to. And so what I'm going to do is these are actually reacting in a ratio. And for this ratio, I can use the coefficients of this balanced chemical equation. And this tells me that 4 hydrogens react to make 2 moles of CH4O. You can easily do this. You could say 100 times 4 is 400 divided by 2 is 200. And you're going to have to start with 200 moles of hydrogen to produce this compound. A lot of people will say, Miss Stewart, I do not have to write all these steps down. I can just look at this and say that there's twice as many hydrogens because 4 is twice as many. Why are you writing all these steps down? Well, it's going to help you on later on because we're going to get to a lot more complicated. And so if you learn how to write all your steps down now, you will be able to do it much easier in the future. And also, every time you write down your steps, you're solidifying that in your memory. So the next part we're going to do is we're going to figure out how many moles of oxygen. Well, I still can only start with moles of CH4O because that's what they gave me. Sometimes I'll have students want to start with moles of hydrogen. I would recommend always start with the data that they give you if you can, because you could have made a mistake in this calculation. So if I have 100 moles of CH4O, and moles of CH4O is going to go on the bottom, and moles, what am I looking for, of O2 is going to go on the top. Well, there's not a coefficient here, so it's an understood 1, and then there is a 2 in front of the CH4O. So these react in a 1 to 2 ratio. So it's going to be 100 times 1 is 100 divided by 2. So you would get 50 moles of O2. Question number 13 is using the same formula from 12. It tells me that a chemist is making methanol according to the problem in 12. They're starting with 24 grams of carbon, 10 grams of hydrogen, and 40 grams of oxygen. In the end, I know that when they make it, they're left over with, they have excess of hydrogen, and they also have excess of oxygen. It tells me there's 2 grams of hydrogen left over and 8 grams of oxygen left over. And the question is wanting to know, what is the limiting reactant? Well, this one is the limiting reactant because I used all of it up, which means once this one was used up, the reaction could not keep going. This is the one that stopped me from making more methanol. If I would have had more carbon, I could have made more, but since I only had 24 grams and I consumed all of it, it is the limiting reactant. Question number 14 gives me this reaction. Yes, I've left off those phase symbols to try to simplify it on my board, but it tells me a chemist is making this N2F4 compound, and this is the reaction that they're using. And I'm adding 150 moles of F2. So I'm starting with 150 moles of this. I like to put my information underneath it. That helps me kind of organize it. And the other bit of information it tells me is that I have an excess of NH3, which basically I'm not going to worry about that. I have as much of it as I want. And the question is asking me how many moles will I make of this N2F4. And so to figure out how many moles I'm going to make, they really gave me one bit of information that I can use, and that's this. So I'm going to start with 150 moles of F2. And I'm wanting to know how many moles of N2F4. And so if you'll remember, these coefficients in front of your balanced chemical equation can act as a ratio. So I'm going to put moles of F2 on the bottom so that way they cancel out, and moles of N2F4 on the top. And the ratio I'm looking for is I'm going to look for the F2, which here is a 5, and the N2F4, which in this balanced equation is a 1. So you're going to take 150 and you're going to divide it by 5, 30 moles of N2F4. Question 15 gives me another balanced chemical reaction. Yes, I've left off phase symbols again, bad habit. But it tells me that I am starting with 150 moles of NaOH, that's like lye, otherwise known as sodium hydroxide, and I have an excess of aluminum. And it's asking me how many grams of this product am I making? This is a two-step reaction. So the only thing I really have that I can start off with is 150 moles of NaOH. Now when I'm going from one part of this equation to the other, I have to remember that these are only used for moles, these coefficients. They're only giving me a ratio in moles. So I cannot use this for moles to grams, but I can go moles of NaOH to moles of Na3AlO3, and then from moles of this to grams of this. So we'll do it in the two steps. So I have moles of NaOH, and I'm going to use my balanced chemical equation. So I put NaOH on the bottom so it cancels out, and put moles of what I'm trying to find my answer to. Remember, if you don't know what to do, always convert to moles first. And so this is going to be, since I'm doing a mole to mole ratio, I'm going to be using my coefficients from my balanced chemical equation. There's a 2 here and a 6. So you're going to be taking 150 times 2, dividing it by 6. That is giving me 50 moles of Na3AlO3. So now I'm going to come down and I'm going to add the second step. You can do this in one long step, but if I'm in 50 moles of Na3AlO, question doesn't ask me in moles, the question asks for it in grams. So I'm going to convert this from moles to grams. You're going to go from moles to grams using your periodic table. So I'm going to put moles on the bottom so it cancels out, and grams on the top. And you're going to get to have the fun of adding up from the periodic table 3 sodiums, 1 aluminum, and 3 oxygens. So when you add all of those up, you get a total molar mass of this compound of 143.95. So your moles are going to cancel out, and you'll be with your answer in grams. You're going to take 50, multiply it by the molar mass. You get 7,198 grams. So as just a recap, we knew how many moles of the we knew how many moles of the reactant we were starting with, and they were wanting you to calculate how many grams of the product. So we had to use the balanced chemical equation to go from moles of one to moles of the other. Then once I was in the mole of the product, I used the molar mass from my periodic table to go from moles to grams. Question number 16, more stoichiometry. The question says, how many moles of sodium are needed to make 500 grams of disodium sulfide according to the following equation? So it tells me I'm starting with 500 grams of this, and the question is asking me how many moles of sodium I'm making. Now, I can't go from grams to moles. I can only go from moles to moles of this. So let's convert this to moles as our first step. Try by yourself. I've got 500 grams and I'm going to moles. So grams to moles, I'm going to be using molar mass that you get from your periodic table. Except you're going to have to calculate it. You're going to have to take 2 sodiums and 1 sulfur and add it up. And I hope you got 78.04. So if I put grams on the bottom, so it cancels out. So in your calculator, you're going to put 500 divided by 78.04. Now, you can keep going with this. Now, you can solve this in 2 steps. I just do it in 1 long step. So the next step is now I'm in moles of Na2S, and I want to go to moles of sodium. When I'm going from moles to moles, I'm going to be using these coefficients from a balanced periodic table. And so 16 moles of Na make 8 moles of Na2S. Moles of Na2S will cancel out. And as long as my units are correct, it should be right. You should get 12.81 moles of sodium. Question number 17 is using that same equation or the same reaction from question number 16. It says, suppose a chemist wants to make Na2S. You're adding 15 moles of sodium. It says I'm adding 15 moles of sodium to 1 mole of S8. And the question is wanting to know what is the limiting reactant? Well, I know technically it reacts in a 16:1 ratio. I don't quite have 16, so the one that is going to run out of first is going to be sodium. So sodium is going to be the limiting reactant. Number 18. So we have this reaction. We're using it to make boron. And if I'm wanting to make 125 grams of boron, how many grams of magnesium am I going to start with? So the goal in the end is 125 grams of boron, and the question is how many grams of magnesium do I have to start with? So this is a multiple step problem. So one of the things you've got to do is first thing they give it to you in grams. I cannot convert from boron to magnesium in grams. I can only do that if I'm in moles, so I'm going to go to moles first. To go to moles, I've got 125 grams of boron, and I'm going to be using the molar mass for my periodic table, and it tells me that there's 10.81 grams of boron in every mole, so grams is going to cancel out, and you're left with your answer of 11.6 moles of boron. So now I'm in boron. I'm going to use my balanced chemical equation to go from boron to magnesium. When I'm going from moles to moles, I'm going to be using these coefficients from my balanced chemical equation. So there's a 3 in front of the magnesium and a 2 in front of the boron. Moles of borons cancel out, and you're going to say 11.6 times 3 divided by 2, 17.4 moles of magnesium. Except it doesn't ask me for moles of magnesium, it asks me for grams of magnesium. I'm going to go to grams. And put moles on the bottom, so moles cancel out. And this is that molar mass from the periodic table. And you're going to end up with 17.4 times 24.31. You get a total of 423 grams of magnesium. What we did is basically they told us I want to make 125 grams of the product, and they asked me how many grams of the reactant I need to start with. But I can't go from grams to grams on using the balanced chemical equation. Things react in moles, or in a ratio of moles. And so I have to first convert this to moles, which was this first step. Then I was able to use the balanced chemical equation to make a ratio to go from moles of boron to moles of magnesium. And once I was in moles of magnesium, you're able to use that molar mass to go from moles of magnesium to grams of magnesium. Question number 19 says a student is making iron chloride according to this reaction. They're adding 50 grams of chlorine and excess of iron. Question is asking me two things. How many grams of the product will you make? And then the next one is actually how many grams of iron are you going to use? So let's do the first part where it's asking for the grams of FeCl3. So the first thing, the main thing they gave me is 50 grams of Cl2. And I can't go from Cl2 to iron chloride in grams. I can only use that chemical equation right there if I'm in moles to moles. So first thing I have to do is I have to go to moles. If you'll remember, chlorine is a homonuclear diatomic, so it's not alone. So you're going to have to take 2 chlorines from the periodic table and add them up, and you'll get 70.9. So 50 divided by 70.9, grams will cancel out, and you're going to be left with your answer in moles of chlorine. I get 0.705 moles of chlorine. Now, don't get lost in what I'm trying to do here. I'm trying to figure out how many grams of iron chloride I'm making. Well, I can go from moles of chlorine to moles of iron chloride. Now, I'm going to get the numbers for this ratio from my balanced chemical equation. So I'm going to put a 3 and a 2. Moles of chlorine cancel out, and you end up with 0.470 moles of FeCl3. It's not asking for moles of FeCl3 though, it's asking for grams of FeCl3. I need to find the molar mass of FeCl3. It is 162.2. So moles cancels out, and you're going to be left with grams of iron chloride. And you should end up with 76.2 grams of FeCl3. So just the first part of the problem here. So I'm going to erase that, and I'm going to solve for exactly how many moles or how many grams of iron is used. I want to know exactly how much of the iron is used, so I'm going to go back to the number they gave me. Yes, I could use the number I calculated, but what if I made a mistake? And so then it would be wrong. So I'm going to use their number of 50 grams of Cl2. I guess I should have saved how many moles that was, but we'll get extra practice. Grams to moles. I do remember it was 70.9, and grams cancels out. I guess I should have saved that from the last equation, but I have 0.705 moles of Cl2. So I'm going to take my moles of Cl2 and I'm going to use the coefficients from your equation to go into iron. And so it is also a 3:2 ratio. And 2 moles of iron reacts with 3 moles of Cl2. So it gives me 0.470 moles of Cl2 cancels out, and that's moles of iron. Now it's asking me to go from moles of iron to grams of iron. So you're going to take that 0.470 moles of iron, put moles on the bottom so it cancels out, and grams on the top, and grams comes from the periodic table. 55.85 moles cancels out, and you're going to be doing 0.470 times 55.85. Final answer is 26.2 grams of iron is consumed in this reaction. The last one, and they gave us like the most complicated reaction we've seen all day, but a chemist is performing this reaction. Even if you have no idea what this reaction is, you should still at this point be able to solve this problem. It's telling me that they have plenty of oxygen, which means excess. I'm not going to run out of oxygen. It also tells me that they have plenty of K2CO3, so we have excess of this. But then it says I only have 115 grams of this reactant. The question is asking me how much of that reactant am I making? I'm going to guess it's probably asking in grams. So I'm going to go from grams of this to grams of that. Now y'all have learned that we cannot go grams to grams. We have to go grams to moles. So there is going to be a lot of calculating here. So you're going to have to add up 1 iron, 2 chromiums, and 7 oxygens from your periodic table. And because I've already done it, it is 271.85. Now you're going to take 115, divide it by that. Grams is going to cancel out, and we're left with moles of FeCr2O7. Now I'm going to do this one in one long step, okay? Mostly because that's just how I did it when I did it earlier. So now that I'm in moles of FeCr2O7, I'm going to go to moles of the product. And so this is where you have to keep your units. So the coefficient here is a 4. I'm going to put it on top of this one. I put FeCr2O7 on the bottom so that they cancel out. And I'm going to this potassium CrO4, and in front of it is an 8. So now if I was working through this, I have my answer in moles of K2CrO4, which, I mean, it would be nice to stop there, but we're not. If I am looking this up on my periodic table, you're going to get 194 grams is the molar mass of K2CrO4. Moles cancel out and you're left in grams. So you can do the multiplication of everything on the top, and you can then divide it by 271.85 times 4. 164 grams of K2CrO4. I don't know, I did that one really fast. But essentially what we did is we went from grams of this reactant to moles. Then we were able to go from moles of this reactant to moles of the product using the ratios from the balanced chemical equation. And once I was in moles of the product, I was able to go back to grams using the molar mass. Good job on the chapter 7 review questions.